with these 4 feeding strategies, there were 2 things that happened with the volumes, okay? The first 3, you have the volume change with the feeding, okay? But the last one, which you have a like much higher substrate concentration adding into the fermenter, you basically have no change in fermenter volumes. Let us see the explanation in terms of the mass balance and what could happen in the case where the fermentation volume change, okay? So when the fermentation volume change, this is how the mass balance will look like. dsdt, okay, you don't have anything out, so that's 0. You don't have a substrate going in. So the substrate would equal to feed of the substrate feed that goes in and minus the substrate that is consumed. Okay. So in fed batch, okay, in fed batch, if substrate feed rate, which is this one, equal to the substrate consumption rate. So that means that you feed in with the flow rate, with the rate that is matching how fast the cells use the substrate. The change in substrate will be 0. Okay, the change of substrate will be 0. So if you put too fast, okay, the cell cannot use as fast as you feed in. The substrate concentration will be accumulated into the fermenter. But if you feed in just enough for the cells to use, so as soon as it goes in, the cell use, as soon as it's going in, the cell use, you see no change if you take sample from the fermenter. Okay, so you don't see any change in the substrate concentration. So the SDT is equal to 0, which is very familiar, right? Okay, because this is what happened with the continuous cultivation. Okay, because at the in the continuous culture, if you reach the steady state, there's no change in substrate concentration too. So the SDT is also 0. Okay, but the SDT equal to 0 doesn't mean that there's no cell growth. So you put in the substrate, the cell grows, just that it uses the substrate fast. So you see no change as soon as it goes in, the substrate is used, but the cell grow. Okay, but at the same time, since what you add make the volume change, so even though the cell accumulated, but the flow that goes in account to the volume that increases in the fermenter. So when you feed in with the XDT equal to 0, you would get no change in cell concentration too. So eventually the XDT also equal to 0. So this is also similar concept to a continuous culture. That is why we can derive that mu in the fermenter, the growth rate of the cells in the fermenter, is about equal to the dilution rate. Okay, so you know that the dilution rate is the feed and volume. Okay, this is a formula for the dilution rate. Okay. When this thing happens, okay, it's similar to continuous culture, but it's not a continuous culture. It's not having like a steady state like the continuous culture has. So in fed batch culture, when this happens, it is called a quasi-steady state. Quasi-steady state is like, it's like steady state, but it's not a steady state. So it's a quasi-steady state. Okay. So that holds true because of the dsdt and dxdt. However, for the product formation, okay, for the product formation, you can't say the same thing with the product formation in this case. Okay, the product formation, the change in the product concentration would depend on a product formation kinetics minus the dilution rate multiplied by the product concentration. So you could still see change in dPdt. Okay, so that is one case for fed batch fermentation when the volume change. So in fed batch, as you see, in fed batch cultivation, you have something feeding in, although you don't have anything taken out from the fermenter until the end of the cultivation. But it also involves the term dilution rate as well, because you add something in, so you are diluting things, so you have a dilution rate. Okay, so the dilution rate in the case where the volume of the fermenter varies. So when you add the first three scenarios, the first three strategy of the feeding, the dilution rate, which defined as F over V, the flow rate divided by volume, the volume changes over time. So your dilution rate in this case will vary as the fermentation goes. And since the flow rate could be constant and the time increase, so the denominator get increased over time, so the dilution rate decrease over time. And since the dilution rate decrease over time and we have quasi-steady state, so the mu decrease as well, okay, over time, if the feeding caused the change in volumes. But if the feeding doesn't change the volume, okay, in the fourth case that I say it's like ideal case for the fed batch, the dilution rate is constant and could be calculated the same way as you do the continuous culture. So this is the idea behind all the three fermentation. Okay. Now, I think most of us familiar with the a batch cultivation and why we do batch cultivation, because like most of the time, like 90-95% of the time when we doing fermentation, either to produce cells or either to produce products, we normally deal with a batch fermentation, because we put things in and harvest out at the end. Okay, continuous fermentation can be used when you want to harvest things continuously all the time. Okay, what about fed batch? I mean, why do we have to do fed batch? Can't we do batch? It's easier because you just put things in at the beginning and take things out at the end, just like the batch. Okay, there is something that helps you determine whether you need fed batch fermentation. Okay, let's see. I want you to see the case in this scenario here. Okay. So in batch fermentation, if you want to, if you know nothing about kinetics of the cells, okay, if you want more products or you want more biomass, you tend to want to put more substrate into the fermentation, okay, and hoping that high substrate will give you more cells and will give you more products. Okay. But it's not always the case. If you know the cell's kinetics, the microbial kinetics, and if you know that a very high substrate could have an inhibition to the cells, to the growth of the cells, you know that putting too much substrate in will put a lot of stress into the cell. Okay, especially something like what we call a substrate inhibition. Okay, you put stress into the cells because say if you put like 200 grams per liter of sugar into your batch fermentation, okay, it's not only a lot of substrate in there, the concentration or the high concentration itself will cause the high osmotic pressure. Okay, I hope you're familiar with like hypotonic solution, isotonic solution, and hypertonic solution, right? So your cells has to maintain its integrity. But if you put it, if it has been put in a high osmotic pressure, which is hypertension to them, it is stressed and it wants to survive, but it's not suitable for them to grow. So maybe they maintain their activities, but maybe they use the sugar, but mostly will go to maintenance. They are not doing anything. They are not growing. They are not producing products. Okay. So if you know the cell's kinetic and you know that it has this limitation, you will not use batch fermentation. And that is the case where fed batch fermentations comes in. Okay. If you want high product and you can't put high substrate in because you know that high substrate will cause the negative effect to your cells because of the stress, you can use fed batch. A commercial production that use fed batch is the production of the baker yeast cell. Like when you want to make bread, you have to put yeast in, right? And the production of that yeast, which is the biomass, is employing the fed batch fermentation because of course you put more sugar in, you will get more cells, but putting a lot of sugar in at once, it will not be good for your cell production. So start off with a lower sugar concentration and start putting more and more and more sugar in to make the cells produce more. So that is a classic example of the use of fed batch fermentation. Okay, so putting a lot of substrate in, if it has a substrate inhibition, a fed batch is a classic solution to eliminate that problem. Okay. So that is the main point for using fed batch. So if you have some sort of inhibition that causes from high osmotic pressure, fed batch could be the answer to those problems. Okay. Okay, so that is all for the fermentation, the mode of fermentation. Okay, we will have a lot of time for any question that you may ask today. But just before that, let I recap something about what we have done in the two lectures. Okay. So basically in these two lectures, the first lecture, we are talking about the microbial kinetics, okay? You could ask questions on that as well if you have a chance to have a look at the videos, which probably can access this morning. We look at the microbial kinetics. We look at the kinetic of cell growth, the kinetic of product formation, the kinetic of substrate consumption. We know how to calculate the basic things like the mu, the QP, and the QS. We we learn how the substrate is used by the cells. Okay, we know that it is used to produce. It can be used to produce products straight away. It can be used to produce energy, provide a cell growth, and along the way produce a product. That 3 scenarios, and we know where the product formation, where the product is formed for. Okay, just how the substrate makes the product. Okay, and understand those microbial kinetics will help you somehow determine the mode of cultivation as well. Okay, an example is just what I had. If you know the microbial kinetic, you know if something has negative effect to the cell, maybe you can choose the fed batch cultivation. Okay, or if you want to use the batch, you know what is the limitation of the use of the substrate and those type of stuff. So knowing these 2 things, the kinetics and mode of cultivation, will help you determine the fermentation that you need. And this is just the introduction into the fermentation technology for those, especially for those who are interested in fermentation process development.